Hello everyone. Today I will be talking about MemLock, a memory usage guided fuzzing technique that specializes in finding software vulnerabilities caused by uncontrolled memory consumption. Coverage-based gray box fuzzing is an effective and practical technique in detecting software vulnerabilities, such as AFL-based fuzzing techniques have been used to find thousands of bugs. However, current coverage-based fuzzing may have blind spots in detecting vulnerabilities caused by uncontrolled memory consumption. Uncontrolled memory consumption is a kind of software security weaknesses. There are three typical uncontrolled memory consumption vulnerabilities, namely uncontrolled recursion, uncontrolled memory allocation, and memory leak. These uncontrolled memory consumption vulnerabilities may be difficult for coverage-based fuzzing to detect, as they can only be triggered by inputs with sufficiently large size or depth. Such input may not be generated by coverage-based fuzzers, as they will unlikely increase the coverage information. I will use two real-world examples to illustrate why it may be difficult for existing coverage-based fuzzing to detect their vulnerabilities. The first example was found by our MemLock. The function recursively calls itself where the input contains a character p. The recursive stats depends on the number of character p in the input. With a sufficiently large recursive stats, the execution will run out of stack memory, causing stack overflow. It can be difficult for existing coverage-based fuzzer to detect this bug. Take AFL as an example. It does not differentiate the change when the recursive stats is greater than a certain value. From the table, we can see that AFL simply discards inputs with a large recursive stats and only maintains inputs with a small recursive stats, making it difficult to find an input that causes the stack overflow. Another real-world example demonstrates an uncontrolled memory allocation problem. A length is extracted from the user input at line 11, and this value is used as the allocation size at line 4. Note that if the allocation size is large enough, the program will fail to allocate the memory, leading to crash or running out of memory. Let's assume AFL already has an input with a small allocation size. If a mutated input tries to allocate more memory, but still execute a covered path, it will not be considered as an interesting input, since it has not increased the coverage. AFL may simply discard such mutated inputs. Therefore, it is difficult for AFL to generate an input with a sufficiently large allocation size that causes the failure. To help detect bugs caused by uncontrolled memory consumption, we propose a memory usage guided fuzzing technique called MemLock that uses a lightweight program instrumentation to collect the program memory consumption information and guide the fuzzing process with memory consumption information. We also propose a novel seed updating scheme to retain the most interesting inputs for each program path. Let us take a quick look at the workflow of MemLock, which contains two main components, static analysis and fuzzing loop. The static analysis decides how to instrument the program and helps collect the coverage information and memory consumption information. MemLock instruments the target program based on the static analysis on control flow graph, call graph, and memory usage operation to obtain coverage information and memory consumption information. After ending instrumentation, MemLock runs the program with generated inputs, collects their memory consumption information, and adds interesting input into the C port through a C updater. Specifically, the fuzzing process is guided by two-dimensional information, the coverage information and the memory consumption information. To offer efficient support for retaining the most interesting inputs for each program path, MemLock updates the CQ in two cases. If the test case results in new coverage, it will be added to the CQ as a new node. This is the same as other coverage-based fuzzers. The difference is that if the test case does not result in new coverage, but it leads to more memory consumption than the corresponding node in the queue, then this node will be replaced with the input that leads to more memory consumption. Let's go back to our motivating examples. For the uncontrolled recursion example, once the newly generated test case triggers a large value of recursive steps, MemLock will update the C port by replacing the old C with new test case that consume more stack memory. Finally, MemLock successfully generates an input that will produce a sufficiently large number of P to run out the stack memory. For the uncontrolled memory allocation example, once the newly generated test case triggers a large value of allocation size, MemLock will update the C port. Finally, MemLock successfully generates an input that will produce a sufficiently large allocation size to crash the program. We have built MemLock on top of AFL and have conducted some experiments against a number of the state-of-the-art fuzzers. We first evaluate the number of unit crashes found by different fuzzers. From the table, we can see that MemLock totally discovered 2009 unit crashes about uncontrolled memory consumption, representing an improvement between 40% and 98% when compared to other baseline fuzzers. Here we show the growth trends of unit crashes found by each fuzzer. We can see MemLock has a static and strong growth trends. We also compare the capability of MemLock to find real-world vulnerabilities against baseline fuzzers. Each vulnerability in our experiment is identified by a unique CVE ID. Here is the first half of the table, and here is the second half. We can see that in most cases, MemLock spend less time in discovering the vulnerability than other baseline fuzzers. MemLock tends to find memory leak with a large amount of memory leakage. This is because MemLock generates inputs that lead to more memory consumption. When memory leak happens, such input will often cause more memory leakage. With MemLock, we have discovered many security critical vulnerabilities, and we have been assigned 15 CVE. At least 12 of them have been fixed, so we are confident that MemLock is viable in practice. In summary, it can be challenging for coverage-based fuzzers to detect vulnerabilities caused by uncontrolled memory consumption. We fill this gap by proposing MemLock, a memory usage guided fuzzing technique that specializes in detecting such uncontrolled memory consumption bugs. If you want to get more detail, please check our paper and also our artifact. That's all. Thank you for your attention.